Welcome everyone. I'm excited to kick off our presentation today. We'll be exploring bridges and culverts, an essential part of our infrastructure. On this first slide, I just want to give you a quick overview of what's ahead. We'll cover the different types, their design considerations, and how they impact our communities. So let's get started and dive into this fascinating topic. A bridge is essentially a structure built to span various physical obstacles you might encounter in the landscape, like a body of water, a valley, or even a road. Its main purpose is to provide a safe and efficient way for people, vehicles, or even trains to cross over these obstacles without difficulty. When we look at different bridges, you'll notice that there are many designs, each tailored to serve specific purposes. Some are built for heavy traffic, others for aesthetic appeal, and some to withstand unique environmental conditions. The design of a bridge really depends on several factors. First, its main function, whether it's for pedestrians, vehicles, or trains, affects its structure. Then, the terrain plays a big role. Building across a deep canyon, for example, requires a different approach than spanning a narrow river. Materials are another key consideration. Steel, concrete, wood, each has its advantages depending on strength, durability, and cost. And of course, available funding can influence what kind of bridge can be built. All these factors come together to determine the most suitable bridge design for a particular situation, making bridges a fascinating blend of engineering, functionality, and adaptability, perfectly aligning with our overall theme of innovative infrastructure. Let's start by exploring some basic concepts in structural engineering. First, a beam. This is a rigid, usually horizontal element that carries loads across a space. Think of a simple wooden plank supporting a shelf. Beams are fundamental because they help distribute forces efficiently. Next, we have the pier. That's a vertical supporting structure, like a sturdy pillar, that holds up parts of a building or bridge. Piers transfer the load from above down into the foundation, providing stability. Then there's the cantilever. This is a projecting structure supported only at one end. Imagine a shelf bracket or a diving board. Those are classic examples. Cantilevers are interesting because they extend outward without additional support at the far end, which makes their design and load management quite special. Now let's connect these concepts. When we talk about a load, we're referring to the weight or force exerted on a structure. Whether it's the weight of the building materials, furniture, or even people, understanding how loads are supported by beams, piers, and cantilevers helps us design safe and efficient structures. Throughout this presentation, we'll see how these basic elements work together to create the resilient structures we rely on every day. Today, I want to talk about the different types of bridges based on their span length. First up, we have what is called a minor bridge. A minor bridge is generally defined as a bridge with a total length of up to 60 meters. It's important to understand this because minor bridges are quite common, especially in less extensive infrastructure projects. Now, when we look at small bridges on rural roads, these are typically considered to be bridges with lengths ranging from about 6 meters to 30 meters. In addition, the span of the individual sections or spans of these bridges usually doesn't exceed 10 meters. This means that these small bridges are often designed to cross relatively small obstacles, like streams or small ravines, and the span length is kept manageable for easier construction and maintenance. Connecting this to our broader discussion, understanding these span length classifications helps us in choosing the right design and construction methods, ensuring safety, durability, and cost-effectiveness. So, recognizing whether a bridge falls into the minor or small category influences how we approach its planning, engineering, and construction. Let's take a closer look at some common types of bridges. First, we have the high-level bridge. This type of bridge is designed with its bottom of deck, or BOD, fixed above the maximum flood level, which we often call MFL. This means that when we're planning such a bridge, we need to carefully consider the highest flood levels to ensure the deck remains above water during floods. The key idea here is vertical clearance, making sure the bridge stays safe and functional even during extreme weather events. Next, we have the square bridge. This type is characterized by its alignment crossing the river at a right angle to the flow of water. Essentially, it crosses directly across the river's width, perpendicular to the direction of flow. This alignment can simplify construction and improve stability, especially in certain terrains. Connecting this to our overall theme, understanding these different types helps us choose the right design based on site conditions, flow dynamics, and safety requirements. Let's talk about skew bridges. These are used specifically where the alignment crosses a river at an angle that is either greater than 90 degrees or less than 90 degrees relative to the flow direction. Essentially, the key point here is the angle between the river's flow and the bridge alignment. The skew angle is measured between the direction of the flow and a line perpendicular to the road's alignment. This creates a skewed or angled bridge, which can be more complex to design and construct. Understanding the skew angle is crucial because it affects the bridge's structural design and construction process. So, when the crossing isn't perpendicular, we need to consider these factors carefully. This concept ties into the overall theme of understanding different types of bridges and their specific design considerations. A footbridge is a specialized type of bridge that is designed exclusively for pedestrians, cyclists, and animals. It's not meant for cars or motorized vehicles, which helps create safe and dedicated pathways for non-motorized traffic. This focus on pedestrians and cyclists is really important because it encourages walking and biking, promoting healthier and more environmentally friendly transportation options. Additionally, by providing a separate space for animals, we ensure their safety and comfort as well. Overall, footbridges play a crucial role in making our urban and natural environments more accessible and safer for everyone, aligning perfectly with the broader theme of sustainable and inclusive infrastructure. A submersible bridge is a fascinating type of bridge designed to adapt to seasonal changes in water levels. During the monsoon season, when floods are common, this bridge actually gets submerged for a certain period. However, what's really interesting is that outside of these flood times, the bridge remains accessible for traffic. So essentially, it's a flexible solution that allows us to keep the connectivity during normal weather conditions, but also manages the challenges posed by heavy monsoon rains. This kind of design is particularly useful in flood-prone areas, ensuring safety and continuous movement. It highlights how innovative engineering can address the natural variability of our environment, aligning well with the overall theme of resilient infrastructure. Now, let's take a closer look at what a causeway actually is. Essentially, a causeway is a paved, submersible structure that can include openings or vents. These openings are important because they allow floodwaters to pass through or over the structure safely. The design helps manage water flow and reduces the risk of flooding or erosion around the area. Specifically, in this context, we're focusing on the causeway across the Vegi River. This structure plays a crucial role in controlling water movement, especially during heavy rains or flood conditions. It's a vital part of flood management and infrastructure, ensuring that water can be directed or managed effectively without causing damage downstream. So, in simple terms, a causeway like this isn't just a road or a bridge. It's a carefully engineered structure that balances the need to allow water flow while supporting transportation and protecting nearby communities. It's a great example of how infrastructure can be designed to work with natural water systems rather than against them. A ford is essentially an unpaved, shallow part of a river or stream bed that you can cross during dry weather or when the water flow is normal. It's like a natural crossing point that doesn't require a bridge or a culvert. When we talk about a ford across a watercourse, we're referring to this specific crossing spot that can be used when conditions are suitable. Understanding where these fords are located and their characteristics is important for planning safe and efficient routes, especially in areas where infrastructure might be limited. So, in essence, a ford provides a practical and accessible crossing option in the landscape, connecting different parts of a watercourse during times of low water. Let's take a closer look at how bridges are classified. First, one common way to categorize them is by their function. This means looking at what the bridge is primarily designed to do, such as supporting vehicular traffic, pedestrians, or even railways. Next, we consider the material of construction. Different materials like concrete, steel, or wood are used depending on the bridge's purpose, span, and environmental conditions. Third, we classify bridges based on their structural type, such as beam, arch, truss, or suspension bridges. Each type has unique characteristics suited to specific situations. Lastly, we look at interspan structures, which focus on how the spans between supports are arranged and connected. This helps in understanding the overall stability and load distribution of the bridge. All these classifications help engineers and designers choose the right type of bridge for a given project, ensuring safety, durability, and efficiency. Let's take a closer look at the classification of bridges, starting with their functions. One key function is to support aqueducts, which are essentially canals built to carry water over obstacles like rivers. These structures are crucial for water supply systems. Next, we have viaducts, which are designed to carry roads or railway lines across valleys or other deep terrains. They help maintain a level path for transportation over challenging landscapes. So, when we think about these types of bridges, it's important to recognize how their primary purpose shapes their design, whether it's for water conveyance or for facilitating transportation across difficult terrain. This classification helps us understand the diversity and adaptability of bridge structures in supporting various infrastructure needs. Today, I want to draw your attention to the Mathur Aqueduct, which is located in the Kanyakumari district of Tamil Nadu. This structure is quite significant because it showcases innovative engineering in the region. The aqueduct was built to facilitate water transport across difficult terrains, helping in irrigation and supporting local agriculture. Its design reflects a blend of practicality and architectural ingenuity, making it an important example of infrastructure development in southern India. Overall, the Mathur Aqueduct not only serves a vital functional purpose, but also highlights the region's ability to adapt and engineer solutions that enhance the livelihood of local communities. A viaduct is essentially a type of bridge, but what makes it unique is that it's composed of several small spans. These smaller sections work together to cross a valley or other challenging terrain. The idea is that instead of building one long, continuous bridge, engineers create multiple shorter spans connected to form a larger structure. This design allows for more flexibility and stability, especially when dealing with uneven or wide landscapes. Throughout this presentation, we're exploring different types of bridges, and the viaduct is a great example of how structural ingenuity can adapt to natural obstacles. It's a perfect illustration of how engineering solutions are tailored to specific geographical features, helping us understand the broader theme of construction adaptability. Now, let's take a look at the classification of bridges based on the material of construction. When we talk about materials, we're really considering what the bridge is built from, which can significantly influence its design, strength, and durability. Some of the earliest bridges were made from timber, which is lightweight and relatively easy to work with, but it does have limitations in terms of strength and lifespan. Moving forward, masonry, such as stone or brick, was also common historically, especially for arch bridges, providing good compressive strength. As technology advanced, iron and steel became popular choices, offering much higher tensile strength and allowing for longer spans and more complex designs. These materials revolutionized bridge engineering, making it possible to build taller, stronger, and more durable structures. In modern times, reinforced concrete has become a staple, combining concrete's compressive strength with steel reinforcement's tensile strength, creating versatile and resilient bridges. Pre-stressed concrete takes this a step further by pre-tensioning the steel reinforcement, which helps to counteract the stresses from loads. Then, we also have composite bridges, which use a combination of materials, such as steel and concrete, to optimize strength and cost efficiency. Lastly, aluminum bridges are used in specific cases where lightweight structures are needed, like pedestrian bridges or temporary spans. Understanding these materials is key because the choice impacts not just the structural performance, but also factors like construction methods, maintenance, and lifespan. This classification helps us appreciate the diversity and innovation in bridge engineering, aligning with the overall theme of understanding different types of bridges and their construction techniques. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at brick and stone masonry bridges. These types of bridges are some of the oldest and most durable forms of construction. They rely on the strength of the materials, bricks and stones, assembled carefully to create sturdy, long-lasting structures. One of the key points here is that masonry bridges are renowned for their ability to withstand heavy loads and harsh environmental conditions. The design typically involves arches or vaults, which effectively distribute weight and provide stability. It's also important to note that while these bridges might require more labor and craftsmanship compared to modern materials, their resilience and aesthetic appeal have kept them relevant through centuries. Connecting this to our overall theme, masonry bridges exemplify how traditional construction techniques still hold valuable lessons in durability and engineering ingenuity. They remind us that sometimes, blending classic methods with modern innovations can lead to truly remarkable infrastructure. Today, I want to talk about iron and steel bridges, which are classic examples of durable and efficient construction. These bridges are primarily made from iron and steel, materials known for their strength and versatility. Their ability to span large distances while supporting heavy loads has made them a popular choice for modern infrastructure. When we look at the key points, it's important to understand how these materials allow for longer spans and greater load-bearing capacity compared to traditional materials like stone or wood. This innovation not only improves safety, but also opens up new possibilities in bridge design. Throughout our discussion, you'll see how the development of iron and steel bridges connects to the broader theme of technological advancement shaping our built environment. These structures truly exemplify the marriage of engineering ingenuity and material science. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the RCC bridge. RCC stands for Reinforced Cement Concrete, and it's a common construction technique used for bridges due to its strength and durability. When we talk about RCC bridges, we're referring to structures that use reinforced concrete to handle both compression and tension forces effectively. This makes them ideal for spanning long distances and supporting heavy loads. One of the key advantages of RCC bridges is their versatility. They can be designed in various shapes and sizes to suit different site conditions and requirements. Plus, the use of reinforced concrete allows for easier maintenance and repairs, which is crucial for the longevity of the structure. In the context of our overall discussion on infrastructure development, RCC bridges are a fundamental component because they connect communities, facilitate transportation, and support economic growth. They exemplify how material science and engineering principles come together to create reliable, efficient infrastructure. So, understanding RCC bridges helps us appreciate the engineering behind the vital connections that keep our world moving smoothly. Today, I want to highlight the concept of a prestressed bridge. Essentially, these bridges are designed to handle greater loads and spans by introducing internal stresses that counteract the forces caused by traffic and environmental factors. This is achieved through a process called prestressing, where high-strength tendons or cables are tensioned before the concrete is placed or immediately afterward, depending on the method used. The key advantage here is that prestressed bridges can be constructed with longer spans, which reduces the need for many supporting piers and allows for more flexible bridge designs. This results in not only a more aesthetically pleasing structure, but also one that is more efficient in terms of material use and durability. Connecting this to our overall theme, prestressed bridges exemplify how innovative engineering techniques improve infrastructure resilience and performance. They are a perfect illustration of how advancing material science and construction methods can lead to smarter, stronger, and more sustainable bridges for our communities. Today, I want to highlight an interesting example of innovative engineering, the aluminum bridge. This structure showcases how lightweight materials like aluminum can be used effectively in large-scale construction projects. Aluminum is known for its strength-to-weight ratio, making it ideal for bridges that need to be both durable and easy to assemble. What's particularly fascinating is how aluminum bridges can be built more quickly and with less heavy equipment, which reduces construction costs and environmental impact. They also offer excellent corrosion resistance, meaning they require less maintenance over time. This example ties into our overall theme of sustainable and efficient infrastructure design. By exploring materials like aluminum, we're opening doors to more adaptable and environmentally friendly construction solutions that meet modern needs. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the classification of bridges based on their structural types. When we talk about the types of structures, we generally categorize bridges into several key groups. First, we have slab bridges, which are essentially flat, simple structures that support loads across spans with a continuous flat surface. Then there are beam bridges, which use horizontal beams supported at each end, making them straightforward and efficient for shorter spans. Moving on, truss bridges are a bit more complex. They use interconnected triangles to distribute forces, providing high strength and stability. Next, arch bridges are notable for their curved structure, which effectively transfers loads into the abutments at either end, often allowing for longer spans with elegant design. Lastly, we have cable-stayed and suspension bridges, which are more advanced and are typically used for very long spans. These structures rely on cables, either directly attached to towers in cable-stayed bridges or suspended from main cables in suspension bridges, to support the deck. Connecting this to our overall discussion, understanding these structural types helps us appreciate how different bridge designs are chosen based on span length, load requirements, and aesthetic considerations. Now, let's take a closer look at slab bridges. These are a fundamental type of bridge that you'll often see in various infrastructure projects. Essentially, a slab bridge is made up of a flat, horizontal slab, usually reinforced concrete, that spans across a gap or obstacle. One of the key points to understand here is that slab bridges are straightforward in design, which makes them cost-effective and relatively simple to construct. They are particularly suitable for short to medium spans where the loads are manageable, such as pedestrian pathways, small road crossings, or even some railway applications. Because of their simplicity, they tend to have shorter construction times and require less complex formwork compared to more elaborate bridge types. Another important aspect to highlight is the structural behavior of slab bridges. They rely heavily on the slab's ability to resist bending and shear forces. Reinforcement within the slab plays a crucial role here, allowing the bridge to carry the loads safely across the span. Connecting this to our overall theme, slab bridges exemplify how fundamental design principles can lead to practical, efficient solutions in civil engineering. They remind us that sometimes, simplicity combined with proper reinforcement and material choice can achieve durability and functionality without unnecessary complexity. Let's take a closer look at beam types. When we're talking about beams, the type you choose can really impact the overall strength and stability of your structure. There are several common types, each with their own advantages and specific uses. For example, simply supported beams are straightforward and easy to construct, making them ideal for shorter spans. Continuous beams, on the other hand, span over multiple supports and help distribute loads more evenly, which can be more efficient for larger structures. Then there are cantilever beams, which extend beyond their supports, allowing for unique architectural features. Understanding these differences is crucial because selecting the right beam type ensures safety, efficiency, and longevity in your project. And as we connect this to overall structural integrity, the beam type directly influences how loads are transferred and how the structure reacts under various conditions. So, choosing the appropriate beam type is a fundamental decision that affects every aspect of your design. Let's take a closer look at the truss bridge. As you can see, it's a classic example of structural efficiency and strength. The key idea here is the use of interconnected triangles, which distribute the load evenly across the entire structure. This design not only makes the bridge incredibly sturdy, but also allows it to span long distances with less material. The truss system is a perfect illustration of how engineering principles can optimize material use while maintaining safety and durability. Throughout our presentation, we've seen how different structures employ various principles to achieve their goals, and the truss bridge is a prime example of leveraging geometry for strength. This concept highlights the importance of thoughtful design in engineering projects, connecting back to our overall theme of innovative structural solutions. Today, I want to focus on the arch bridge, which is one of the most iconic and historically significant types of bridges. The key feature of an arch bridge is its curved structure, which effectively distributes weight and provides strong support. This shape allows the load to be transferred from the deck down through the arch and into the supports or piers at either end. What makes arch bridges particularly interesting is their ability to handle heavy loads while using fewer materials compared to other designs. The arch naturally channels the forces outward and downward, creating a stable and durable structure. Throughout history, arch bridges have been used in many cultures, from ancient Rome to modern engineering projects. They beautifully demonstrate how understanding natural shapes and forces can lead to innovative and resilient construction. In the context of our overall discussion on structural design, the arch bridge exemplifies how form follows function, using geometry to optimize strength and efficiency. It's a perfect illustration of engineering ingenuity that combines aesthetic appeal with practical performance. Let's take a look at some examples of cable-stayed and suspension bridges, which are fascinating structures in modern bridge engineering. One notable example is the Hooghly Bridge in Kolkata. This bridge showcases the impressive design and engineering that go into creating these types of bridges. Cable-stayed bridges, like the Hooghly, use towers from which cables radiate down to support the deck. This design allows for longer spans and a more elegant appearance. Suspension bridges, on the other hand, rely on main cables draped over towers with suspenders holding up the deck, enabling very long spans, ideal for crossing wide rivers or deep valleys. The Hooghly Bridge is a great example of a cable-stayed bridge, balancing functionality with aesthetic appeal. It plays a crucial role in connecting different parts of Kolkata, facilitating transportation and commerce. Understanding these types of bridges helps us appreciate how engineering innovations open up new possibilities for infrastructure development. They are not just feats of construction, but also vital components of urban growth and connectivity. Let's take a look at how bridges can be classified based on different key aspects. First, we have the interspan structures, which include simple, continuous, or cantilever bridges. These classifications are mainly based on how the spans are arranged and supported. For example, simple bridges have a single span, while continuous bridges have multiple spans supported without hinges, providing greater stability. Cantilever bridges, on the other hand, extend horizontally and are supported only at one end, often used in situations where supporting piers are difficult to build. Next, we consider the position of the bridge floor relative to the superstructure. This is an important design aspect that affects both the aesthetics and functionality of a bridge. We have decks, which are level surfaces for traffic, through bridges, where the roadway passes through the structure with supporting towers or piers on the sides, half-through bridges, which are a hybrid, with part of the structure passing through and part supporting the deck, and suspended bridges, where the deck hangs from cables, allowing for longer spans and elegant designs. Finally, the method of connections plays a crucial role in the structural integrity and construction process of bridges. Connections can be pin-connected, riveted, or welded. Pin connections are flexible and allow rotation, often used in movable bridges. Riveted connections, common in older structures, involve bolted joints that are riveted in place, providing good strength. Welding, which is more modern, involves fusing materials together to create a continuous structure, offering high strength and durability. Understanding these classifications helps us appreciate the complexity and versatility involved in bridge design, ensuring we select the right type for each specific project. Now, let's take a closer look at how bridges can be classified based on different factors. First, when we consider the flow level, we often categorize bridges as high level, especially submersible bridges. These are designed to allow water to flow beneath them, often used in areas with significant water movement. Next, regarding navigation, we look at whether the bridge is a high-level or a transporter bridge. High-level bridges are built above water or land obstacles to facilitate smooth passage, while transporter bridges are a bit more specialized, used primarily to carry people or vehicles across difficult terrain or water. When it comes to the length of the bridge, we have several categories. Culverts are shorter, usually less than 6 meters long. Minor bridges range from 6 to 60 meters, serving smaller crossing points. Major bridges are those exceeding 60 meters, and long span bridges are designed for very wide crossings, often over large bodies of water. Finally, the purpose and use of the bridge also help classify them. Some are permanent structures meant for continuous use, others are temporary, serving short-term needs or construction purposes. There are also military bridges, which are designed for rapid deployment and strategic use in defense scenarios. By understanding these classification criteria, flow level, navigation type, length, and service purpose, we gain a clearer picture of the diverse types of bridges and their specific roles within our infrastructure. This slide doesn't contain enough information. That's why we're moving to the next slide. So, when it comes to the method of connections in bridge construction, there are a few common approaches we should consider. One of the primary methods is using pin connections, which allow for a certain amount of movement and flexibility. These are often used in structures where some degree of rotation is beneficial. Next, we have riveted connections, which involve joining components with rivets that are hammered or pressed into place. Riveted joints have been traditional in steel construction and provide reliable strength, though they are somewhat labor-intensive to install. Finally, welded bridges are a modern and widely used method. Welding fuses materials together at the joints, creating a continuous structure that offers high strength and rigidity. All these methods, pin, riveted, and welded, are crucial because they influence the overall stability, durability, and construction process of the bridge. Understanding these connection types helps us see how different design choices impact the integrity and longevity of the structure, which ties back into our overarching theme of efficient and resilient bridge design. When selecting a site for a bridge, one of the ideal choices is a straight reach on the upstream and downstream sides of the proposed location. This helps ensure stability and easier construction. The permanency of the channel is also crucial. We want a site where the river's course is stable over time. A steady river flow without cross currents simplifies both design and construction, reducing potential issues during and after the project. It's best to choose a narrow channel with firm banks, as this provides better support and minimizes erosion risks. When considering the width of the channel, we need to ensure it's adequate for the expected flow, and the average water depth compared to the maximum depth gives us an idea of the flow's variability and the potential for flooding. Sharp bends upstream of the site are generally avoided because they can cause turbulent flow and complicate construction. The site should also be free from obstructions on both the upstream and downstream riverbeds, such as rocks or debris, which could hinder foundation work or cause damage. Another key point is to stay away from the confluence of tributaries. These areas tend to have complex flow patterns and can be more prone to flooding. A high, stable bank is preferable because it offers better protection against erosion and flooding. When designing crossings, a right-angle crossing is generally preferred because it simplifies construction and reduces structural complexity. Curves in approaches or along the length of the structure should be minimized to avoid unnecessary complications and costs. The distance between a railway bridge and a highway bridge should be as wide as possible, ideally at least 400 meters, to ensure safety and ease of construction. For skew crossings, A skew of more than 45 degrees should generally be avoided, as higher angles can complicate design and increase costs. Additionally, we need to consider the geological conditions. The presence of hard rock or other erosion-resistant strata close to the riverbed is very advantageous, as it provides a solid foundation and reduces erosion risks. Economical approaches are also vital. The site should be free from obstacles like hills, frequent drainage crossings, sacred areas, graveyards, built-up zones, or troublesome land acquisition issues. All these factors influence both the cost and feasibility of the project. Finally, the approach roads should be designed to minimize flood risks and avoid difficult terrain, ensuring smooth access for construction and future maintenance. By considering all these factors thoroughly, we can select a site that's not only structurally sound, but also cost-effective and sustainable in the long run. Now, let's talk about the selection criteria for choosing a bridge site during the preliminary study, which is part of the techno-economic feasibility survey. First, we consider the topography of the area. Understanding the landform is crucial because it influences the design and construction methods we can employ. Next, the catchment area is important. It tells us about the water flow and potential hydrological impacts on the site. Hydrology itself is a key factor, as we need to assess water levels, flood risks, and flow patterns to ensure the bridge can withstand environmental conditions. Geotechnical data is also vital. This includes soil type, stability, and bearing capacity, which directly affect the foundation design. Seismology cannot be overlooked, especially in earthquake-prone regions, because it helps us determine the seismic risk and appropriate engineering measures. Navigation is another critical aspect, particularly if the bridge spans a navigable waterway, as we need to ensure sufficient clearance for vessels. Construction resources, meaning availability of materials, labor, and equipment nearby, influence project logistics and costs. We also look at nearby bridges, because their presence can impact the site selection, either by providing precedent or highlighting challenges such as congestion or structural interference. Traffic data is also essential, as understanding current and projected usage helps us design a bridge that meets future demands efficiently. Overall, these criteria form a comprehensive framework that guides us in selecting the most suitable site, balancing technical feasibility with economic viability, and aligning with the broader project goals. Let's take a closer look at culverts. A culvert is essentially a structure that allows water to pass underneath a road or railway. It's a crucial component in drainage management and infrastructure resilience. When designed properly, culverts help prevent flooding and erosion, protecting both the infrastructure and the surrounding environment. They're often made from materials like concrete, steel, or plastic, depending on the specific needs of the project. One of the key points to remember is that the size and capacity of a culvert must match the expected water flow to avoid potential issues like water backup or overtopping. In the context of our overall theme, culverts exemplify how thoughtful engineering solutions help us manage natural water flow effectively. Properly designed culverts are vital for maintaining transportation safety, environmental health, and infrastructure longevity. So, understanding their function and importance is essential in our broader discussion on sustainable infrastructure. Let's talk about culverts. A small bridge, which might have 3 or 4 spans, with each span not exceeding about 3 meters, is called a culvert. Now, when we consider highways, especially where culverts are constructed to cross small distributaries, the span length can be a bit larger, around 4.5 meters. Similarly, in railway tracks, the maximum span length is typically kept around 6 meters. A culvert usually consists of several key components. These include the abutment, which supports the structure, wing walls to guide water flow, arches or desk slabs that form the main structure, parapets for safety, and a foundation to support everything. Inside the culvert, there may be floor pitching, which is basically a lining or coating on the bed drain. Whether this is provided or not depends on the soil conditions and the flow velocity of the stream water. If the soil is weak or the water flow is strong, floor pitching might be necessary to prevent erosion or damage. Overall, culverts are designed carefully to ensure efficient water passage and structural stability, connecting seamlessly with the overall drainage and transportation system. Now, let's take a look at the different types of culverts commonly used in construction and infrastructure projects. First, we have the pipe culvert, which is one of the simplest and most widely used types. It's essentially a cylindrical pipe that allows water to flow beneath roads or railways. Next is the box culvert, which is shaped like a rectangular or square box. It's often preferred for its strength and ability to handle larger flows or heavier loads. Then there's the arch culvert, characterized by its curved, arch-like shape. This design provides excellent strength and is often used in areas where the terrain or aesthetic considerations are important. Moving on, we have the slab culvert, which is basically a flat, slab-like structure, suitable for short spans or where space constraints exist. Finally, the beam and slab culvert combines beams with a slab to create a strong, versatile structure, especially useful for longer spans or varying load conditions. Understanding these different types helps us select the most appropriate culvert for each specific situation, ensuring durability, safety, and efficiency in our infrastructure projects. Let's take a closer look at pipe culverts. These are typically used for very small drainage works, especially when passing through embankments of roads or railways. You'll notice they usually consist of one or more pipes placed side by side, forming a conduit for water to flow through. The materials used for these pipes can vary. Common options include wood, steel, reinforced cement concrete, and cast iron, each chosen based on the specific requirements of the project. An important aspect of installing these pipe culverts is ensuring they stay in the correct position against the force of water. To achieve this, the pipes are often secured with masonry work at both ends, which helps retain their position and provides stability. Sometimes, instead of masonry, stone pitching is used for this purpose. Overall, pipe culverts are a simple yet effective solution for small-scale drainage, seamlessly integrating with road and railway embankments while providing reliable water passage. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about box culverts. They are often the preferred choice for construction, especially when working in loose soil conditions or when larger spans are needed. These culverts can be used for a single span of about 3 meters or for a double span that totals around 6 meters in width. However, it's important to keep in mind that beyond that, say over 6 meters, box culverts tend to become less economical. When designing these, the thickness of the RCC slab is a key factor. Typically, it should be kept within a range of 1.25 to 2.5 meters to ensure strength and durability. Most box culverts are constructed with rectangular or square openings, which makes them quite versatile. And an interesting point is that these culverts are usually made from precast RCC materials, which allows for quicker installation and quality control. Overall, box culverts are a practical solution for specific situations, especially when large spans and difficult soil conditions are involved, fitting well into the broader scope of our infrastructure development. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about arch culverts. These structures involve constructing a superstructure in the form of arches, which is quite interesting. The design is similar to that of masonry bridges, relying on the strength of the arch shape to carry the loads effectively. One key point to remember is that arch culverts typically do not have piers on the sides of the opening, which makes them different from other types of culverts. This absence of piers helps in reducing obstructions within the flow and allows for better water passage. Overall, arch culverts are a clever and durable solution, especially suited for crossing small to medium-sized waterways, where a strong, arch-shaped structure can efficiently handle the loads and water flow. Let's talk about slab culverts. These are typically constructed for spans up to about 2.5 meters in width. The key idea here is that the slab itself forms the superstructure of the culvert. To build it, we place either a stone slab or a reinforced cement concrete slab directly over the simply supported beams that rest on piers or abutments. Now, what's interesting is that these slabs act as the main load-bearing component, creating a solid, continuous structure over the culvert opening. And just like with permanent bridges, we also include features like parapets and wing walls. These not only enhance safety by preventing debris from falling into the culvert, but also help in managing water flow and protecting the structure itself. Connecting this to the overall theme, slab culverts are a practical and efficient solution for small-span crossings, combining simplicity with durability. They are an essential part of our infrastructure toolkit, especially in situations where a quick, reliable crossing is needed without the complexity of larger bridge structures. Let's take a closer look at the wing wall. Wing walls are an important structural feature that extend from the main wall or structure. Their primary function is to direct or contain the flow of water, soil, or other materials, helping to manage runoff or stabilize embankments. You'll often see them in bridge abutments or retaining walls. What's really key here is that wing walls contribute significantly to the overall stability of a structure. They help distribute loads and prevent erosion or shifting of the main wall. When designed properly, they not only support the integrity of the structure, but also enhance safety and longevity. Connecting this to our broader theme of structural resilience, wing walls exemplify how thoughtful design elements can improve performance under various conditions. They might seem simple at first glance, but their role in ensuring durability and safety is crucial. So, understanding the purpose and proper implementation of wing walls is essential in our overall approach to robust engineering solutions. Now let's talk about beam and slab culverts. Their layout is quite similar to that of a big girder bridge, which many of you might be familiar with. The main difference lies in the specifics of the span length, the number of spans, and the size of the structural components used. Typically, culverts of this type are smaller than girder bridges, which makes them suitable for different applications. So, while the overall concept and design approach are comparable, the key distinctions are in these dimensions and structural details, tailored to fit their particular functions within infrastructure projects. This slide doesn't contain enough information. That's why we're moving to the next slide. When designing a culvert or a bridge, it's essential to consider several key factors to ensure safety and efficiency. First, the construction site itself plays a crucial role. Its location, accessibility, and environmental conditions will influence the design choices. Next, the alignment is important. We need to make sure the structure integrates smoothly with the existing or planned infrastructure. Another critical aspect is the discharge capacity, how much water or flow the culvert needs to pass through without causing flooding or erosion. The number of spans also matters, as it affects the overall stability and the materials we'll use. Finally, the foundation is fundamental. A solid foundation ensures the longevity and safety of the entire structure. By keeping these considerations at the forefront, we can create designs that are not only functional, but also durable and well-suited to their specific environment. This holistic approach ties back to our overall goal of building resilient and sustainable infrastructure.